Thanks. Well, good morning. So today I'll be presenting on regional hydrogeochemistry and also a little bit around case studies. The talk's going to really be around what we've done so far, what we can do in the region around here. So we've currently got a project we're collaborating with the survey with. They've taken 300 plus samples to the east of Mount Isa block in the cover region. And a lot of this talk is going to be around what we can do and will do with that data. However, we're going to start off looking at the regional hydrogeochemistry data sets and then sort of zoom in on a few case studies. So, value of hydrogeochemistry then. Why are we thinking about doing this? Why have we been doing it for the last 10 plus years in CSIRO? I suppose I should say, really start off with this work was begun well, way back by Angela Giblin, but David Gray is really the one that put together a lot of the data sets you'll be seeing. And then that's been taken over by now Nathan Reed as the person at CSIRO who has taken the hydrogeochemistry forward, and he's asked me to present some of this today. So why is it something of value? So really it's more of a, certainly on that regional scale, more of a Greenfields exploration tool, something to develop regional targets that can be later followed up by other exploration techniques. It's potential for low sample density. So most of these samples are taken from station bores. They're taken close to the surface, 10 meters. And with the data sets that you see we put together, we try to keep that consistent across the entire region, whether it's either our CSIRO database or, as you see, we're brought in other databases from the states as well. You also have a potential there to see through cover. So because you've got a water-rock interaction that's quite a large volume, you're also sampling water that can be down 40, 50 meters at the water table. There's quite a nice likelihood to see through cover. And I'll show you a couple of case studies where we've shown that quite well. And of course, yeah, that moving interfaces, as we'll see. Now, what are some of the things we can look for? Those indicators of alteration. Look for those halos in different types of elements. So arsenic, tungsten, for example. Uranium shows up really nicely. And as you might expect, some of the indicator minerals you normally see in soil samples are also present within water. However, some of the ones that you might normally use for like nickel, copper, zinc in water aren't as good as you might hope and might expect. And we'll go through that a little bit in the talk. I'll start off then looking at the Australia-wide hydrogeochemistry data set. So this is something that, as I say, David Gray really spent a lot of time putting together. It now contains, I think, 380,000 data points across the entirety of Western Australia. And this isn't just an exercise in bringing them together and putting them in a spreadsheet. There's a lot of QA, QC and validation that's gone into this data set to create something that should be seamlessly available across every state and with a high degree of confidence, or as high as we can, in being able to quality control each of the elements within this, this data set. So that then is now available and can be used. There's both sources on the CSIRO online publication portal, easily Googleable. Just search for this and it will come up, and you'll have both the documentation and the data is all downloadable. What you don't get there are a lot of the indices, as you'll see through there, and saturation things, but all the primary data is available. And most recently, it's just gone onto the BOM website. So they have a mandate to hold groundwater data. So this is perhaps one of the easier, if you just want the data without any of the background stuff, this also holds it now. Nearly all the data is a few little bits still to go on. In terms of what we can provide, if anybody's interested in hydrogeochemistry data and actually taking the samples themselves, Nathan Reed here, and of course talk to myself, has exploration guidebooks for actually taking the water samples, and we recently developed an Android app. So a lot of the surveys, so we've done a bit of work with surveys, a number of different companies actually take the app, it's all free, we support that, and do that water sampling themselves, but give us the water samples if you want to, and we can take it from there. Or indeed just tell you what labs we normally use and do it that way. So let's actually have a look at a bit of the data. What are the sort of things we're getting out from this? So for example, some of the major elements, most of these data points will have pH, EH, sulfate, TDS, that sort of thing. Not every data point has all the elements you might wish for, and we'll see that as we go through. But things like pH very much are consistent to the system. You see some major patterns, for example, the salinity down, the increase in pH in the south of Western Australia. And that brings up some issues as we go through. You see that even though because it's more acidic, it generally holds more metals, so an anomaly in an acidic water isn't the same as an anomaly in an alkaline water, for example. But if we look at these elements in terms of the data densities, as I say, sulphate to chloride, that's really quite nice. It shows some major variations. We'll have a look at this again in a bit later. Supposed to highlight here it's sulphate to chloride ratio because you want to take away the effect of salinity issues because that increases potential to decrease sulphate. But as we go through these, you'll see that the data density decreases. So things like lithium, a fairly decent spread. You can see there's some nice high values out here in east of Mount Isa. As we go through, you'll see things like cobalt, which really would be quite interesting to have more of, is really quite limited in terms of where the data is, and is one of the main reasons we've working with the survey here to help increase the data density we have in the cover near these locations. There's not only those data densities, but there's also a real relevance of scale. So, for example, we look at this sulphate to chloride ratios. Now, sulphate's interesting because obviously where your sulfides, you produce an increase in sulphate in the water. And not only that, but you can also have an anomaly is essentially a high sulphate or a low sulphate value. So, for example, pyrrhotite to pyrite weathering will decrease your sulphate, actually uses the sulphate, and pyrite weathering will produce the sulphate. So an anomaly is something either high or low in the system. So in this example here, we have the Jaguar Bentley Teutonic Bore mineralization. And you can see here this anomalous sulphate picks up quite nicely these deposits. And indeed, this sample was taken before Bentley was known about, so David always used to pick this one as something where we'd actually seen it before it was known. Now, as I mentioned before, the direct metals themselves aren't always that useful. Things like copper and zinc drop out of solution very quickly, they bind with iron oxides, and you don't form large halos with these elements at all. What you do see when you're right in the guts of the deposits, so this is Jaguar Bentley again, you do see these anomalies, but you have to be pretty much in the sulfide to find them in the copper and zinc. So that means we look for other indices, other different elements we can use, and as I mentioned, sulfate works very nicely, giving a broader dispersion to broader halos. Nitrate works really well, so nitrate acts as an oxidizer in many of these elements, in none of these waters, so a depletion in nitrate is an anomalous thing that could be related to mineralization, and we can also produce indexes. So, for example, the iron sulfide index is manganese, iron, EH, pH combined together to produce a better signal, if you like, of anomalism within those waters. Or is also implication for health and baseline data for water and groundwater in these regions. So, for example, here we have very high fluoride concentrations just east of here. And this has come from all those statewide data sets that we've shown. Similarly then, you've got that really high fluoride, but you also have really high dissolved tungsten concentrations out in the waters to the east of here as well. Don't know what it means at the moment. Hopefully we can update you as the project continues. But is there a potential for mineralization within the system with high tungsten, high fluoride? But it also demonstrates the robustness of different anions such as fluoride, vanadium, moly, and tungsten as we go through. So a few of those are more interesting than those direct elements associated with mineralization. Just to show you some more of these indexes rather than just using the elements themselves, this is a fairly simple one. Gold, arsenic, and silver together produces a index that quite nicely picks up some of the major gold deposits in WA and up into the Capricorn region through here. So we can pick out major camps using indices and hydrogeochemistry through the system. And indeed, if you then zoom in, this is Agnew, and we can see here we've got the mineralization itself quite nicely defined and an anomaly away from mineralization, and where there's none, you don't see anything in the water. So it quite nicely proves, in this case, even on the prospect scale, hydrogeochemistry can be used to define mineralization. So I just wanted to give you a few examples around the broad hydrogeochemistry, different levels of data we have within the data sets, moving down into different scales as well, how different indices can be used. And now I just wanted to give a couple of examples around that seeing through cover. So why are we using this to see through cover as well as just as a regional sampling tool? So this is some of the region I've been working in recently, up in the Capricorn region in Western Australia. We've got the Ilgam Capricorn here, moving up into the Proterozoic, Paleoproterozoic basins in the Capricorn. And really the area of interest we're looking at is this chromium anomaly through the Bryah Basin here. The Bryah Basin is defined in this system. You see the chromium anomaly here related to mafic rocks within that basin. We put on the top the GSWO soil sampling through here. See a similar pattern. Background is generally higher anyway in chromium, but this anomaly of chromium actually cuts off at an earlier point, if you like, than the chromium in the waters. Now if we go and look at the AEM, we can actually define a paleochannel system here that runs through the base of the Bryah Basin, and you get increasing cover as you move towards the west system. And what we're actually seeing is in the water that you can see that chromium through that cover. So this is a 50 metre depth slice. So you're seeing through about 50 metres of cover in the water that you don't see in the soil sample. That's quite a nice example of that seeing through cover. And similarly then I just wanted to point out the Abra lead zinc deposit. That's actually within those Avon Collier basin sediments. And that's at a depth of around 400 metres. Now, we're probably not seeing through 400 metres, there's probably some other related mineralisation above that, but we're definitely seeing through a significant amount of cover here with an anomaly in lead and zinc, and lead and tungsten, and we definitely don't see that in the soils. So this is the lead anomaly over Abra. You see here is the scale, that's 4.5 kilometres, and you're seeing anomalous data that ranges 7-8 kilometres above this deposit in this case, which is in a basin in a significant amount of cover. So we're quite happy with those examples, being able to see through 50, 60 metres easily, and probably more than that in some cases. Now that won't always be the case, it depends how the aquifers are defined and whether they're connected through the system. But there's definitely that potential there. I also want to highlight some other more novel, if you like, techniques. So you can use the direct elements, you can use indices, and you can use saturation of different minerals, which I haven't really gone into in here. But you can also use isotopes. And isotopes are another way of defining whether or not the waters have been in contact with mineralization. So in this case, we're actually looking at the sulfate that is potentially weathering from a sulfide. And we're looking at the sulfur and oxygen in that sulfate. So here's a map of 300 odd sample points through this Capricorn origin. And we see that there are some areas highlighted in here where we've got anomalous values, and again, high or low, blue or red would be anomalous within this system. And similarly, the oxygen on those sulfates also show a number of anomalous values. Now, quite often they relate to the lithology, but where you see things like, so for example up here, see the Paulsens Gold deposit, which we'll just zoom in on. Paulsens Gold deposit, 1 million ounce gold deposit. And we can see here quite a nice halo in it up to start off with in gold, platinum, palladium and cobalt. And that runs out to about a couple of kilometres from the deposit itself. And then we can also look at those sulphur and oxygen isotopes again. You can see here they're anomalous, but if we plot them up in the background data set, we can see there's a really distinct population here within the sulfate and the oxygen isotopes that sits very much differently compared to the rest of that population. And indeed, if you look at the pyrite within the Paulsen system, you see that the pyrite sulfur values sort of fit within that population. And we can do that for a number of different deposits in that region, where you see the sulfide weathering seems to, on many cases, relate to the sulfate in terms of the sulfur isotope composition. So yeah, we can look at the elements, we can look at indices, we can look at the saturation of different minerals, and we can also do things with isotopes. So there's the sulfur, and we can do oxygen, hydrogen on the water itself as well. There are a number of different aspects, a number of different techniques we can bring together to help target these regional potential areas of interest as we generally define them. So, Mount Isa region. This is the spread of data we have in some of the major parameters, not even elements in many cases. So in this case, this is pH, and we see that we've got slightly more acidic waters than Mount Isa block, Moving into the more alkaline region to the east, we have sulfate. So sulfate chloride, and the sulfate, as you might hope, starts to pick up some of the more major deposits in the area and weathering those sulfides. But what we don't have, and while we're working on the server, is pretty much anything else. So we haven't got any of the lead, we haven't got any of the silver. That might be because it was never taken, never analysed, or it's been deemed due to the QA/QC process that it's just not reliable at all. So we've got another 326 samples, I think, that have been taken through this area. Sampling's complete. The samples are with us, so that is a report to look out for in terms of how we interpret that data, and really let's just detailing that. This is a sort of map that we normally come out with in terms of areas of interest through a region with the hydrogeochemical data. So many of these points will be anomalous in multi-elements and multi-points. Some of them, things like gold. Gold's a very good indicator of gold mineralization, so a single point gold anomaly is something of interest. And similarly there, for example, we've got a major lithium anomaly over here in the west of the Capricorn region, which has led to those tenements being taken up recently. So that's a sort of map that we would produce to define areas of interest and reasons behind that, based upon a lot of the work that I was discussing earlier. So, valuable deliverables to date. I think really, as I've gone through, I've tried to summarise these. We've got direct concentration of target metals. And as I said, sometimes those aren't really reliable, such as copper and zinc. They drop out the solution too quickly, but then we use these things like the ionic charcoal fluoride, arsenic, antimony, moly, tungsten. We can produce saturation indices, good for uranium, but we can also use sulfate, nitrate, chromium, bromide. So these actual weathering of sulfides within the systems, and produce mineral indices that together produce a better anomaly than you'd have individually. So how can we help? So I hope, to some extent, that this data is available. It's easy to download from these sources. You can put it in and plot it up pretty quickly in a GIS program, just to see if there's anything in your region that might have interest. The new samples that might be collected and will be collected have been collected. The survey can be easily put in context very quickly in terms of a regional background, and we have an understanding of what those signatures mean in terms of ethology and potential mineralization within the region. And we also have the app that's supported by predominantly Nathan, which helps actually sampling these waters. That's it.